All right, welcome back to The Effect. So this chapter, we're talking about these scary things that are always around us, no matter what kind of causal inference design we are doing, that we do need to worry about, although many people would prefer not to have to think about them. And sometimes they try not to think about them and then things go bad. But in this video, we're going to be talking about one that pops up quite a bit, which is missing data. So what missing data is when you have a variable and you have a bunch of observations, but some of your observations do not have all of the values filled in. So for example, let's say I'm doing some sort of census study, and I know how many people are in your household. I don't know how many people live in your household. I know what your income is. I know what your race is and your gender. And I also want to know whether you're married. But for some reason, I don't have that variable in the data for you. It doesn't say that you're married. It doesn't say that you're not married. It just says, I don't know. That's a missing value. Now this can be a problem because if I want to do a study on the effects of being married or whatever, or the things that predict whether you're married or not, well, what do I do with this person? Well, they're not married, they're not unmarried. I can't do statistics on a value that I don't have. So a common approach to what people do is they will just drop anybody who has missing values of the relevant variables from their data. So I'm like, I'm going to do this study of marriage. I don't know whether you're married or not, so I can't really do much about you. So I'm just going to ignore you entirely and drop you from the data. This is called list-wise deletion. This is the most common way of dealing with missing data. Now, whether or not this works depends on a number of different factors. Importantly, why the data is missing, which means that you really have to think theoretically about why you think this variable might not be written down for this particular individual. The first main way in which somebody could have a missing value is if they are not in universe. That is, the question does not apply to them. So for example, let's say you have a variable in your census type data of what is your occupation? What job do you have? Are you a carpenter? Are you a plumber? Are you a teacher? Are you whatever, right? There's another variable in there that says, do you have a job? Now let's say that you have answered no to that question. You do not have a job. Well, then why would I bother asking you what your job is if you don't have one? You would be not in universe for the which occupation do you have job. If that's happening, list-wise deletion works perfectly fine. You are simply not the kind of person to whom this question applies, so we're probably pretty good. Another explanation for why the values might be missing is the rosiest and sunniest of them, which is missing completely at random. A value is missing in a sense that is missing completely at random if it is missing for entirely random reasons, completely unrelated to everything. It just so happens that this value wasn't written down, right? There's no reason or rhyme, it's just randomly happening. Now, why might this occur? You know, maybe you had the data all stored in a file cabinet and some of the files got wet, right? And that's just sort of random. Or, you know, maybe it just, you knocked on the door that day and you didn't write it down, or the thing got smudged or whatever. It's random. There's something completely unrelated to anything. There's no reason why it's missing. It just happens to be missing. When this is going on, then yeah, list-wise deletion also works fine. Then we get into the slightly scarier ones. Then we get to missing at random, which is confusingly very similar to the words for missing completely at random, but an entirely different concept. I apologize. Missing at random says that the reason why the value is missing is related to some of the variables, but that you can measure and control for those variables. You can account for those variables. You can predict why somebody is missing. Let's say we're looking at that marriage variable, that we have a missing marriage value for some people. Let's say that there happens to be a religion out there that forbids telling people whether you are married. Like you're not allowed to tell the government that whether you're married or not. That's a thing just for our religion to know. Nobody else can know, right? And maybe that's going on. So in that case, we would not observe a marriage value for those individuals, but I can tell you why they're not observed. It's because they're in this particular religion. So if I've written down elsewhere what religion they are, and I can say, oh, this religion doesn't report their marriage values, that's why this is missing, then that is missing at random. So it's random once I account for those other variables that I know explain why it is missing. Now in that case, you can still do some stuff. You know, list-wise deletion doesn't quite work, but there's a couple of other methods that I'll talk about afterwards that do work a bit better. And so all the methods I'm going to talk about after I explain this list-wise deletion stuff and the different reasons for missing at random, that will help really apply in our missing at random case. Finally, we have the scariest version, which is missing not at random. And a value is missing not at random if the reason why it is missing is related to the value of the variable itself. So let's say, for example, that people are embarrassed to tell a survey taker that they're not married. So in that case, you might have some missing values, and the people who are missing are way more likely to not be married. It's like, hey, if I'm married, I'll tell you about it. If I'm not married, some people are going to tell you, and some people are like, I'm not going to answer that question because they're embarrassed for some reason. So in that case, the value of the variable itself is related to the fact that it is missing, and that's the hardest case to deal with. And in that case, list-wise deletion could really mess you up. But in that case, there's also not a whole lot you can do. So we've got these 4 different reasons why values might be missing, just getting rid of values that are missing, getting rid of observations with missing values, only really works that well in the first 2 of these cases. What are some other things that we can do to help deal with missing data? There are a few different approaches that we can use, probably the most common of which is what's called multiple imputation. Multiple imputation says, hey, I have a missing value, I'll just use what else I know about you to try to predict what that value happens to be. Before we get to multiple imputation, let's think about simpler versions of imputation. So for example, something that a lot of people do is something called mean imputation. So let's say that we are looking at income, and let's say that your income value is missing. And I'll say, well, I don't know what your income value is, but I'll just take the average of everybody else's income value, and since I don't know which one you are, I'll just give you the average value. I'll pretend that you have the average value. That doesn't work very well, but that's sort of the starter idea of what we are doing here, right? We're making a prediction for you, and we are filling in your values based on some other information that we have. So what a single imputation would be is that, okay, I'm not going to give you the average value for everybody, but I am going to predict what your value is using your other data. So I might try to make a model that predicts what your income would be using all the other variables, estimated using everybody else's data, and then I will use that to predict your income, right? I will plug in your values, I'll predict your income. That is a single imputation. Multiple imputation takes that exact same idea, but it repeats the process a bunch of times, adding noise in there, which tends to improve the predictive quality of the results. You end up with, let's say, 10 or 20 different predicted values for your income, and then when you go to estimate your model, you just run the model 10 or 20 times and then average those models together to get your results. Now, multiple imputation is one nice way of going after missing values. It works if your data is missing at random because you are using the other values in that data to help to make that prediction, right? So in the extent to which your other variables explain why you're missing, it will incorporate that into its predictions. Doesn't work quite as well if things are missing not at random because it is not able to incorporate those sorts of unobserved, the actual value itself, right? If the value itself is likely to be different for people who are missing as opposed to people who aren't, well, it's not incorporating that into its model. It can't, right? Because it doesn't have any data on the missing people. Additionally, it's doing this imputation without really recognizing the model that it will eventually be used for. There are some other methods that more properly take into account why you are imputing the data and might give you more purpose-built fill-in values. One of those approaches is called limited information maximum likelihood. So maximum likelihood is an estimation method that we haven't actually talked about a whole lot in this book, although it is underlying some of the methods that we have used. And the basic idea of it is, I got this model, and that model would generate some data if I ran it, right? If I got a model and I randomly generated some data with it, it would be likely to generate certain things. I can then pick the parameters of the model that makes the random data that it would generate as like the actual data that I have as possible. I'm maximizing the likelihood of seeing the data that I do in fact see. That's a very basic rundown. But what limited information maximum likelihood does is it says, okay, we have some missing values for certain people. So not everybody can fully contribute to my estimation of how likely I think the data is. But you can still contribute based on the variables you do have, right? And so I'm going to take what I can from each individual, leaving out the parts that I cannot see because they are missing, and I will estimate the model in that way. So limited information maximum likelihood is a way of not imputing the missing values, but estimating the model, taking into account the fact that we don't have the full data for everybody. Another approach to this same basic idea is the expectation maximization algorithm and its application to missing data. This is another approach that really uses the model itself to do some of the imputation for us. The way the expectation maximization algorithm works is sort of goes back and forth between 2 different estimation processes. It starts by estimating a model, and this model can generate some likely values, right? Based on this model, here's what I think your most likely income is if you are missing your income. Right, so then I've predicted an income for you in the data. And then I will go back and I've got this predicted data. I'm going to use that to re-estimate the model based on the values that I filled in. So you sort of go back and forth between using the data that you have to estimate the model and using the model that you have to predict what the missing value should be in the data. You go back and forth a few times to try to get yourself the best version of the model that you can. That's the expectation maximization algorithm. Now, all of these really work best in missing at random or missing completely at random scenarios. The stuff that you can do to deal with missing not at random, there are some methods you can use, but they're a bit complex. I'm not going to go into them in this video. But that is the basic rundown of missing data. We have to think carefully about why we think the data might be missing. If we're lucky, maybe we can just drop the values that are missing and go about our day, which is in fact what most people do, whether it's a good idea or not. We can also try to use some methods that really respect the missing values and try to incorporate as much as they can of the data that we have, even if some values are missing. Multiple imputation fills in values based on what we predict them to be. Both limited information maximum likelihood and expectation maximization algorithms, they use what we can have to start to sort of work with the model to estimate the model using as much information as we can possibly get out of it. All right, that is how we can deal with missing data, or at least a very basic primer on it. Thank you.